Okay, so this is the second talk about Riemann-Roch. Last time I told you the statement of the theorem and also made some calculations to show that it is reasonable to believe that this is true. So let me quickly remind what we did. So Riemann-Roch theorem, as I told you, is a theorem about compact Riemann surfaces. But you can also make it algebraic and talk about smooth projective curves over not necessarily algebraically closed fields, any field. But for the moment, I want to stick with the case of compact Riemann surfaces because intuitively it's easier to understand what are the objects that we want to study. So we wanted to understand the dimension of certain space of functions that was defined using a divisor D. This is the space of all meromorphic functions where chord P of F plus chord P of D is bigger than or equal to 0 for all P. So we saw that this is a vector space over C, and we also saw that if it let little l of D to be its dimension, it's going to be a finite dimensional vector space. And the Riemann-Roch theorem is about studying this dimension. How can we calculate this dimension using topological properties of the Riemann surface and also the properties of the divisor D? So what we saw was that L of D plus a point is either L of D or L of D plus 1. Depending whether you can find an element F inside L of D plus P0 minus L of D. If such an element exists, then the dimension increases by 1. If no such element exists, then the dimension remains the same. And from this, it's easy to deduce by an induction that L of D is always less than or equal to degree of D plus 1. Where the degree of a divisor is the sum of the multiplicities of the points that appear in that divisor. So not only we understand that this dimension is finite, but we have an upper bound for this value. Now, what Riemann actually found was a lower bound on L of D. He actually proved that L of D is always bigger than or equal to degree of D plus 1 minus the genus. And the genus of a compact Riemann surface was something very interesting because there are many different approaches to define this genus. The easiest way probably is by the number of handles. So if you have a Riemann surface, which looks like this, you just count the number of handles or holes that this Riemann surface has. That's going to be the genus. So here you have a genus 3 Riemann surface. But you can also define it as the dimension of space of holomorphic one forms on X. Or you can also define it as the dimension of the first cohomology of X with coefficients in the structure sheet. Now this looks a little fancy. I told you that this is the same as the dimension of the space of obstructions for a problem which is called Mittag-Lefler problem. So I explained to you what this problem is previous time. It's about finding meromorphic functions that for a finite number of points on the Riemann surface, you have their singular behavior. You have their Laurent expansion for negative terms. And for other points on your Riemann surface, they have to be holomorphic. So over C, such a problem always has a solution. That means that there is no obstruction. And the reason for that is that C is part of the CP1, the sphere. In the genus, there is 0. So the dimension of the space of the obstruction is 0. So that means that there is no obstruction to solve multi-Lefler problem. But once you go to higher genus, then there will be obstructions. I'm going to talk more about this probably today. And these three definitions are going to give you the same answer for a number, for an integer, which is called the genus. And the equality of these numbers is also non-trivial. So this is during the process of proving Riemann-Roch theorem, we're going to see why these different ways of defining genus agree with each other. So let me just give them names. This is topological genus. This is called geometric. And this is called arithmetic. The notation that they use is P sub G or P sub A, G for geometric and A for arithmetic. Many of these definitions have the ability to generalize to higher dimensions. For example, if you have a compact complex manifold of dimension n instead of 1, which is a Riemann surface, then you can define the dimension of the space of holomorphic n forms of X and call it geometric genus. Or here, you can take the nth cohomology of X with coefficients in OX and call that arithmetic genus. And there are relations between geometric and arithmetic genus. Actually, in higher dimensions, the arithmetic genus is usually defined using some sort of Euler characteristic, not just H1, but some alternating sums of dimensions. So I don't want to go really into the higher dimension business. I just want to mention that these definitions have ability to generalize. Okay, now I want to tell you a very naive way of the way that Riemann actually arrived in this inequality. And I want to give the intuition behind the reason that the genus appears in the number or the dimension of the space L of t. So to make things simple, let's take a divisor to be a sum of certain points. So distinct points. Not every divisor is in this form, but this is an assumption that is pretty mild. In fact, since I told you that you can replace a divisor by its equivalence, using this, sometimes you can get a divisor which is not originally in this form to make it look like this. So in the Riemann-Roch theorem, it's a theorem that you can always replace a divisor by something that is linearly equivalent to it because nothing in that formula changes. The terms in the formula of Riemann-Roch remains the same if you change D with another divisor that is equivalent. Okay, now L of D has a very simple description. It's the space of meromorphic functions with poles only on x1 up to xd and only simple poles. So you have a function or you have a map from this space to C to the power D that sends F to the residues at these points. Okay. The residue of a pole or a simple pole is the coefficient of 1 over z when you expand expanded in Laurent expansion. So the only negative term that appears in the Laurent expansion for f around xi is 1 over z. Like z is the coordinate, local coordinate where x1 becomes 0. And therefore, you have these well-defined complex numbers. And if you think a little bit, you see that the kernel of this map is C. And let's think together why this should be true. If a map f, a function f, goes to 0, that means that it has 0 residues at all these poles. And since these poles are simple, that means that these are not really poles. So that means that the function f is holomorphic at x1 up to xt. It's also holomorphic at other points. And therefore, f is a holomorphic function on the entire space x. And we all know, because x is a compact Riemann surface, there are no non-constant holomorphic functions on x. This is a result that follows from Liouville's theorem, or there are other ways to prove it. But this is a well-known fact. And therefore, you see that dimension of L of D is at most D plus 1. This is something that we already knew because we saw that in general, even D is, if D is general, not just a sum of distinct points, dimension of L of D is always less than or equal to degree of D plus 1. But one can make it more precise if one knows what is the image of this map res. Okay. So if you knew what the dimension of this image is, then L of D would be 1 plus that dimension. So what we want to really understand is that what kind of restrictions do we have to see if I give you a vector of D elements in C, can I construct a function whose residues at the poles x1 through xt are those numbers? Do we have any obstruction for this or not? And you can see now why the Mittag-Leffler problem actually plays a role in the Riemann-Roch theorem. This is exactly the type of problems that Mittag-Leffler asked. We want to know the singular behavior of a function at some points, and we want it to be holomorphic everywhere else. To the surprise, actually, any holomorphic one form, omega, gives such a constraint. So if you give me one holomorphic one form, such as omega, then what I can say is that the sum of the residues of f times omega at all points is 0. This is a theorem that also was mentioned in the previous lecture. For any meromorphic one form, the sum of the residues of this meromorphic one form over all points of x is 0. And the reason for that is Cauchy integration formula that tells you that the integral of a one form along a closed path is equal to 2 pi I times the sum of the residues of all the points that lie inside that closed path. So if you take this closed path in such a way that it contains all singularities of omega, then the sum will be 0, because you can either think of this path that covers these singular points or outside this path. The Riemann surface was compact. So both ways are legal. And this shows that the sum of residues of any holomorphic one form, any meromorphic one form is 0. Now, why does this give you a constraint? Because since omega itself is holomorphic, the residues only appear at points where F has simple poles. So this is nothing but sum of residues of F at P times the value of omega. Okay, so each holomorphic one form gives you a linear equation on the space where the image of this map res lies. So since we know that there are G of these omegas that are independent, so we get G independent equations. And therefore, each of them will reduce the dimension at most by one. And therefore, we have L of D is bigger than or equal to 1 plus D minus G. Okay. Why don't I say that it's equal? Because I don't know whether these are all the constraints. These are some of the constraints that we have. And when I say it's bigger than equal, it's smaller than equal. Hold on. Okay. Yeah, bigger than equal. And for this, I want to, okay, so I want to claim that these are all the constraints. So this is the part that actually I'm not going to prove right now. We're going to see its proof in its due course. But it's believable that, actually you see why the genus should appear. So the dimension of the space of holomorphic one forms is somehow related to the dimension of the obstructions for solving Mittag-Leffler problem. That's the equality of geometric genus and arithmetic genus. And you might ask, okay, the actual Riemann-Roch was this: L of D is equal to 1 plus D minus G plus L of K minus D, where K is the canonical divisor, which was the divisor of any meromorphic one form, any non-zero meromorphic one form, which is the sum of the order of vanishing or pole of this omega at P times P. And now you might ask me why such a term should appear. Why is it actually natural to expect the existence of such a term to correct Riemann-Roch theorem? And that's the actually contribution that Roch actually made. Riemann only had the inequality on top, and Roch actually proved it in a more precise way using the canonical divisor. And the reason is, you see, not all these equations are essential. If you have a actually holomorphic one form that vanishes at all points P that are on this divisor x1 to xd, then this equation is redundant. So the equation sum residue at xi f omega of xi I equals 1 to t equals 0 is redundant for omegas that vanish on all. And this means that if you write this omega primes, for example, if you write this omega prime as f times omega, where omega is the one that you chose to construct the canonical divisor, this means that f belongs to L of d minus k, k minus d. Right? Because if you look at the definition of L and the definition of K, you see exactly those F's, which are inside this space, give you meromorphic one forms omega primes or holomorphic one forms omega primes that vanish on all x's. And therefore, you have as many of these redundant equations as you have in the dimension of the space, and therefore you have to add this step. Now, this is not really a complete proof, but I really want to give you this advice. When you have a theorem that is not very trivial, you should have a very intuitive proof, even not precise or completely correct, to tell you why this theorem should be true philosophically. And I think these calculations are the ones that was done by Riemann himself. And he was convinced that this is a true theorem. And of course, he had some proofs, but his proofs was not, in our standards, for today's standards, considered to be completely rigorous. But probably if he wanted to make them very rigorous, he could. But during those times, it wasn't fashionable to write proofs as rigorous that we write it today. Okay. Now, I want to go back to more rigorous math and tell you a little bit about how to complete the proof of Riemann-Roch theorem using a calculations that I did at the end of previous lecture. Namely, I assume that my Riemann surface X is given by a polynomial equation inside CP2, where P is a reducible homogeneous degree equal n polynomial. And also assume that the equation that it defines is non-singular, meaning that the gradient of P is defined as partial derivatives of P with respect to X, Y, and Z is not zero on X. In fact, it's not too hard to show that if you have a point where all these partial derivatives are zero, then P, that point must be on X. The reason is that there is an Euler formula that you learn in calculus, in Calc 2 maybe, that relates a homogeneous, the partial derivatives of a homogeneous polynomial, and it's the polynomial itself. If you have some, say a monomial x1 to the power r1, x2 to the power r2, xm to the power rn, we call it p, then derivative of p with respect to x1 multiplied by x1, derivative of p over x2 multiplied by x2, and so on, is going to be equal to m times or degree of p times p. degree of P here is R1 plus R2 plus Rn. So in other words, if you have a point where all these partial derivatives vanish, then P also must vanish. But that's not that's an important issue. Anyway, so we know that this condition implies that we get a complex manifold of dimension 1, and therefore you get the Riemann surface. And using Riemann-Horvitz formula that I also mentioned in the previous lecture, you should be able to find the genus of this curve. And genus of this curve is given just in terms of this degree. It's going to be n minus 1 times n minus 2 divided by. Okay, so in this very explicit case, I can prove for you the Riemann-Roch theorem rigorously and without any flaws. If you accept that this is enough for you, then you can forget about the rest of this lecture and go home. But if you want to see proof that works for any field, and not necessarily even algebraically closed, then you have to spend some more time on algebra and understand what discrete valuations are and how Dedekind Weber defined the notion of a Riemann surface just in terms of the function field without even the space. I'm going to talk about that also today. All right, so what did we do in the last lecture? It was this. We took a line ax plus by plus cz equals 0 inside CP2, and then intersect this line with x. It's going to have some finite number of points as its intersection. And in fact, if you count the number of multiplicities of these intersections of any point with its any point on the intersection of these two subspaces, you will get n, which is exactly equal to the degree of the equation that defines x. The reason is that there is a theorem by Bezout that says if you intersect two equations, the number of points in common is equal to the multiplication of their degrees. And you have a degree 1 and a degree n, so you get n points. So you get a divisor here, which I called h, which is defined in this way, where I of p is the multiplicity of the point p as an intersection point of L intersection with x. So this is a positive divisor because the multiplicity cannot be negative. So it's a positive divisor. And we saw that actually the class of this divisor is independent on the choice of this line. If you choose another line, L prime, you get a different divisor, but the two divisors are equivalent. And the function that gives you this equivalence is the quotient of these two equations. So the divisor of this f is h minus h prime, where h is the divisor that is coming from the top equation, and h prime is the divisor that's coming from the bottom equation. Okay, what else did we see? We saw that L of mh is going to be larger than or equal to the number 2 choose m plus 2 minus 2 choose n minus n plus 2. And this was proved also in a very simple and elementary manner. Namely, if you give me any homogeneous degree n polynomial q of x, y, and z, we get the function q of x, y, and z divided by ax plus by plus cz to the power m, which belongs to L of mh. Why? Because if you take the divisor of this function and add mh to it, you get the divisor of the function q. And the divisor of the function q, that means the intersection of the points q with the Riemann surface, is a positive divisor. So L of mh is by definition those functions for which if you add the divisor of f with mh, you get a positive divisor. And this function f here has this property. And therefore you might say, okay, so since I have to choose m plus 2 such degree m homogeneous polynomials, then we must have at least this many functions inside L of mh. This is not completely correct because some of these functions will give you zeros. And these are exactly those that are multiples of p, where p was the equation that defined your equation x, your Riemann surface x. So I have to subtract those, and this is the second term is coming from those terms. So in other words, you ask when two of these functions are equal, and the answer is when their difference is a multiple of p. And this difference can be easily calculated. This is mn plus 1 minus n minus 1 n minus 2 divided by 2. And you see that this is degree of mh plus 1 minus the genus. And this is indeed Riemann's inequality, proved now rigorously without any fact about the obstructions to Mithak-Leffler problem, and to know that actually the holomorphic differential forms give you all such obstructions. And but the drawback is that we haven't really proved Riemann's inequality for any divisor. We have proved it for these particular types of divisors, m times h. So our next job is to see how to generalize this proof from this particular divisor to a general divisor. So how can we generalize this proof work for any? And I'm going to prove actually for you much stronger result. I'm going to prove that L of d minus L of k minus d is bigger than or equal to the degree of d plus 1 minus the g. And once I prove this, the Riemann-Roch theorem follows just by a very trivial observation of replacing d with k minus d here. If this is done, Riemann-Roch follows right away. Namely, replace d with k minus d. So what do we get? We get L of k minus d minus L of d is bigger than or equal to the degree of k minus d plus 1 minus g, right? And we already calculated degree of k. That was 2g minus 2 minus degree of d plus 1 minus g. This is going to be g minus 1 minus degree of d. So you multiply it with minus 1, you get L of d minus L of k minus d is less than or equal to g minus, the degree of d plus 1 minus g. So we have proved that it's bigger than or equal to this, and we have proved that it's less than or equal to this. So we must have equality, and therefore we have Riemann-Roch. So all I need to show is to show that this inequality holds. Now I have shown for you that this inequality holds for MH. Let me write it one more time here for you. L of d minus L of k minus d is bigger than or equal to degree of d plus 1 minus g. So this is true for MH with M large. The reason is that when M is large, degree of MH is very large. Degree of MH is Mn. And when k minus d becomes with negative degree, then there is no function in there, and therefore the dimension is going to be 0. We saw this at the first time I defined for you this little L of d. I said one of the most basic properties of it is that when the degree of the divisor d is negative, this number is 0. And okay, so for these MH, we have shown that L of MH is bigger than degree of MH plus 1 minus g, and the other term is actually not existent, and therefore this is true here. Another fact is this. For any divisor, D, for example, the sum of Ni Pi minus sum of Ni Qi, we can find points x1, x2 up to xr such that MH is equivalent to D plus x1 plus x2 plus x. So this, let me write this as a little fact. So in other words, I can make MH equivalent to D with some additional points added to it. Let's try to prove this. So somehow I want to get rid of these negative terms. What I do is that I take lines AIX plus BIY plus CI Z equals 0 that pass through QI, okay, and add D with the divisor of this function, A1x plus B1y plus C1z to the power n1, A2x plus B2y plus C2z to the power n2, and so on. You divided by ax plus by plus cz to the power of m, where m is the sum of these numbers. So that this really becomes a function. Because if you want to define a function on CP2, you have to have a quotient of two homogeneous polynomials of same degrees. Okay. And what does happen if you do this? Then M1 Q1 will disappear, M2 Q2 will disappear, and so on. And then you would have this equal to D plus a positive divisor minus MH. So so that means that MH will become D yeah. So it comes like this. Not equal, but equivalent. So that's actually the proof of this fact. Maybe I didn't really explain it so well, but if you think at home, you see that it's not really anything to it. I mean, the fact is, you can make these negative terms disappear by choosing the divisor of your function very accurately in a very precise way, and you only have positive terms. In fact, I read somewhere that both Riemann and Roch only worked with effective divisors in their formulation. So they assume that the divisor has only positive coefficients. And this assumption was not very critical because you can always replace your divisor with something else so that this holds. The degree of the divisor doesn't change. You can choose one point to have all the trouble of negative coefficients. But anyway, I mean, I think that once you know the Riemann-Roch theorem for effective divisors, then from there to prove it for a general divisor is a very, very short kind of argument. Okay, now how far away we are from the actual Riemann-Roch? Not much, actually. So we know the Riemann-Roch theorem for MH, and we know that any divisor can be made into MH by adding points. So all you need to show is that this inequality, so the lemma, the inequality L of D minus L of K minus D bigger than or equal to degree of P plus 1 minus G is true for D if it is true for D plus P. So this is actually backward induction. You go from a bigger divisor to a smaller divisor. Now, why this finishes the proof? Because we know that the inequality is true for MH. So it's true for D plus X1 plus X2 plus XR. And then using this lemma, we can one by one remove the Xi's and arrive the truth of this inequality for D. So since it is true for D plus X1 plus X2 plus XR, then according to the lemma, it has to be true for D plus X1 plus X2 plus XR minus 1. And again, by the lemma, it has to be true for D plus X2 plus X1 plus X2 plus XR minus 2. And then you can kill off these terms one by one until you arrive at D. And okay, now let's see why this lemma should be true. So if we go from d plus p to d, how much decrease we have in L of p minus L of k minus d? If I can show that we have at most a decrease by 1, then we are done. Because the degree of d is decreased exactly by 1, and this is, if this is decreased at most by 1, then the inequality will remain true. So I need to show that this will be decreased at most 1. I need to show this decreases at most by 1. Right? Think about it a little bit. The right-hand side of the inequality, when you go from d plus p to d, will be decreasing exactly 1. And if the left-hand side decreases at most 1, then of course the inequality remains true. So what do we know about these numbers L of d and L of k minus d? We know that L of d and L of k minus d decrease at most by 1. So the only situation where we have a decrease more than 1 is when let me try to write it. Okay, so I want to say L of d minus L of e minus sorry. K minus d is bigger than or equal to L of e plus p minus L of k minus d minus p minus 1. Okay, that's what I want to prove. That's the meaning of this will be decreased at most by 1. Now, the only case that this doesn't happen is when L of d plus p is equal to L of d plus 1, and L of k minus d is L of k minus d plus minus p plus 1. Right? That's the only case that this doesn't happen. In that case, this difference would be decreased by 2 instead of by 1. Remember, these numbers will be increased or decreased at most by 1 by adding or removing a point. So the difference of these two is at most 2, but I want to say that the difference of these two is at most 1. So you have to see exactly when this 2 happens. And if you think a little bit, this is just elementary school arithmetic. This happens when a situation like this occurs. Now, what does this mean? This means that we have a function f in L of p plus p minus L of p, and we have a function g in L of k minus p minus p minus p minus L of k minus p. And now what happens if you multiply these two functions? You get a function fg, which belongs to L of k plus p, and it's not in L of k. Okay? So what does this mean? This means that you have fg times omega Remember, omega was that one form that defined K. Divisor of omega is K. And if G times omega is a meromorphic one form that is holomorphic everywhere, except a P that has a simple pole. Right? Because it's in L of K plus P. So that means that if you add the divisor of F with K plus P, it becomes positive. So that means that at any points other than this particular P that we added to K, Fg times omega is going to be holomorphic. And at this particular point P, it's going to have only a simple pole, a simple non-trivial pole. And so far, everything is good. You might expect, okay, so what? We have such a one meromorphic form. But if you think about the fact that the sum of residues must vanish, you see that this is impossible. Because this meromorphic one form has residue 0 everywhere, except at this one point P that has a non-zero residue. And this cannot be canceled because that's the only place that it has a pole. Therefore, you see that it's a contradiction, and therefore such a situation cannot happen. And I was right to say that the left-hand side will decrease at most by 1, and the right-hand side decreases exactly by 1, and therefore the inequality remains true. And the proof is done. As you see, the main ingredient in this proof was one thing, the sum of residues equals 0 for a holomorphic one form. And this is completely a transcendental fact because we proved it using integration, Cauchy integration. And Cauchy integration does not exist over a general field, for example, over a finite field. And another fact that we used was the computation of degree of the canonical divisor K. We used the fact that this degree is 2g minus 2 somewhere. Oh, remember here, when I said replace d with k minus d, and then you see that you get the inequality in the reversed order. Here I calculated degree of k that I already calculated using Riemann-Roch. Riemann-Roch is also a transcendental fact. Of course, these, both of them have algebraic analogs. I mean, the meaning of residue generalizes to general fields, and you can define the residue of a rational one form. And what else I wanted to say? Yeah, and Cauchy integration also can be made algebraic. And the fact that the sum of residues is 0 is true also in general. Okay. So maybe I can stop for a few minutes, and then you can stop actually the recording, and I can answer some questions now. Okay, now I want to try to get rid of some of my assumptions. For example, I want to get rid of the assumption that my Riemann surface was given by a simple polynomial equation. Also want to make the way to generalize this method for other fields, not just C. And to do this, I want to talk more about this Metag-Leffler problem. So I want to prove a version of Riemann-Roch that probably is due to Riemann, and says this, that L of D is degree of d plus 1 minus I of 0 plus I of d, where I of d is the degree, the speciality of d, and this is a terminology coming from 19th century, and this means that the dimension of the space of obstructions to Mittag-Leffler problem in modern language, it's the dimension of the first cohomology of X with coefficients of OX of D, where OX of D is the line bundle associated to D. I defined it in the previous lecture also. And since I don't want to talk about cohomology today, I want to try to define it in other terms. So to do this, I'm going to define a ring for you called Adels, which is the product of Kp over P. Now, what is Kp? Kp is localization or completion of the field K with the discrete valuation given by OP. Now, I have to tell you a little bit about these terminologies, and these are things that actually was the notion of Adel was defined first by Weil in order to prove Riemann-Roch. It was previously used by other people, namely Chevalier, to do class field theory. And class field theory usually is considered to be part of number theory, not algebraic geometry. But today, class field theory is both for number fields and function fields, and even for schemes. And the analogy between number fields and function fields was first recognized probably by Dedekind and Weber in that famous book that I told you about in the previous lecture. I have brought the book with me. The translation of this book in English exists. I don't know if you see it. This is called A Theory of Algebraic Functions of One Variable, and it was written in 1880. And I think, and many people agree with me, that this is one of the most important papers written in algebraic geometry. This is the transition from the very concrete calculational way of thinking of algebraic geometry to more abstract way of doing algebraic geometry. And they are very much ahead of their time. After publishing this paper, actually, algebraic geometry didn't progress in this fashion, in an abstract fashion, and it waited until mid-1950, for example, or in 1940, when Andre Weil and other people like Grothendieck and Serre came along and continued their work. So instead of working with the Riemann surface, Dedekind and Weber worked only with the field of meromorphic functions on the Riemann surface. And the notion of point on a Riemann surface was replaced by these discrete valuations for P. And these discrete valuations actually used to define a norm or a metric on K, where you define this to be like some number E minus 4P. Doesn't matter what number you use. Any number bigger than 1 will do. I use E. And this fact that the sum of 4P of F becomes 0 for all P translates into the fact that the product of these numbers is 1. And this is some sort of product formula. Later on, actually, Artin and Waltz showed that fields that have these product formulas, I think similar to this ones, are only number fields and function fields. And therefore, the common feature between number fields and function fields is this product formula. And many things that are common between number fields and function fields actually follow from this product formula. Okay, and now, so if I want to give you a similarity between this function field case and number field case, I have to talk about Q, for example, where any prime number will give you discrete valuation is the exponent of P in X, and then you define the absolute value of X with respect to the prime number to be P raised to the power minus 4P of X. And now the product formula doesn't hold if you only take primes, because there is also a usual absolute value, which is called the non-Archimedean prime. Archimedean prime. Therefore, you have this product formula. So you have to include infinity also. So the difference between the function field case and number field case is existence of these infinite primes, which they do exist in number field and they do not exist in function field. And you might say, okay, this is a very small difference, but the fact, for example, that Riemann hypothesis is proved for function field case but not for number field case, probably due to the existence of these infinite primes. So they actually caused a lot of trouble. And that's why usually people tend to think that number fields are much more difficult than function fields. So analog of theorems in the function field case usually are proved in much earlier or much easier fashion than the ones in number fields. Okay, now you probably also have seen how to get from Q to p-adic numbers, where you look at all numbers like these. And these formal sums make sense because once you're working with this absolute value, then they're converging and they have a limit there. And this is actually the way that you learn from your first year analysis course, that if you have a metric space X, you can make it into a complete metric space where all Cauchy sequences converge. And here is the same thing. You have a metric space Q and you make it into complete metric space. But the reason, the fact that this addition and multiplication are continuous with this metric, they remain continuous, they extend here. So the extension is not just the metric space, but it's a field with these operations of addition, multiplication, division, subtraction, and so on. So you can do this here for the field of meromorphic functions on a Riemann surface. And this is also, this here is Laurent expansions. at P. So it's local Laurent expansions at P. And this means that you have really an embedding here. And inside here you have the subring OP of holomorphic. Functions at P. The same way that you have ZP here. So when I talk about this restricted product, I mean all these FPs where all P of FP is bigger than 0 for almost all P's. So except at a finitely many points P, where your function, I shouldn't say function, the component at P can have poles. For other components, the function is holomorphic. So if you do the same construction for Q, you would say that the tuples where the P component is in QP, and for almost all P, this P component is in ZP. Okay, and this is called Adels. And it has a topology, which I'm going to define for you. The topology is not the one that's coming from the product topology. And the reason for that is that although these KPs are locally compact, when you take the product of infinitely many locally compact spaces, the answer, the result will not be locally compact. And we want this Adels to be locally compact. And why do we want that? Because there is this theory of power measures on the locally compact groups and rings. And once you have this Haar measure, you can do analysis. I should say that although the Adels and Idels were defined in 1930s, when people were doing classical theory, the real use of Adels and Idels came by the work of Tate in his thesis, when he reproved some of the results of Hecke using this language of Adels and Idels. In fact, his thesis was one of the few theses that didn't have anything new. Anything that he proved in that thesis was already known to Hecke. And the only new parts of his thesis was the method. But I would say that many people agree that his thesis was one of the most important theses in 20th century, mathematical thesis in 20th century that really revolutionized the field of studying L functions. Anyway, now, how do Adels help us to rephrase Riemann-Roch that it also works not for C but for any field? Is this. We define this notion of A of D, where this is the FPs for chord P of FP plus chord P of D is bigger than or equal to 0. And you see that it's very similar to the definition that we had before. L of D is the F such that chord P of F plus chord P of D is bigger than or equal to 0. And indeed, the relation between the two definitions is that L of D is A of D intersection with K. Now you might ask, okay, what is K? Because A is the product of KPs, and do we have a copy of K in there? The answer is yes. You have a copy of K inside the Adels, and this is the one that you just diagonally embed K inside Adels, because any meromorphic function that you have on the entire space X will give you local components. And the local components has only poles at finitely many places, and therefore really you get an element of the Adel. So these F is holomorphic at all p's except finitely many points, and therefore you get really a point in that.
What is
And
here?
question?
What is D here?
D is a divisor. Now, what is a divisor? Divisor is a formal sum of points. And what are points? Points are the discrete valuations. So once you have a function field K, you can define the points on K to be all discrete valuations of this field up to equivalence. And then define divisors and all the things that you already defined in the case of a Riemann surface, and do everything again using this more abstract language. Okay. Now, let me give you a lemma. If P1 is bigger than or equal to P2, then of course A of P1 will contain A of P2, and the index, or should I say dimension, is equal to the difference of the degrees. So at this point, I am going to only discuss the case when the ground field is C, complex numbers, and we're working again with a Riemann surface. So we start with the Riemann surface X, we take K to be the field of meromorphic functions on this, and then we construct adults from this, and then all the rest. But what I want to really emphasize is that the choice for C here is not really critical. I mean, I can easily generalize these things for other fields. You have to be a little bit careful about how to define the degrees and things like that. But I'm going to spend a little time telling you how to do it. Don't worry. So I'm trying to make my proof a little bit more abstract so that step by step I extend it to a more general case. All right. So let's try to prove this lemma. And it's enough to show that A of B plus P over A of B is 1. Right? Because D1 is obtained from D2 by adding points. Each time you add a point, you increase the dimension by 1. So the difference of the dimensions, I mean the dimension of the quotient, will be equal to the differences of degree of D1 minus degree of D2. Degree of D1 minus degree of D2 is the number of points that you need to add to D2 in order to arrive to D1. Okay, and this is very simple because the only differences that you have here is at the point P. So instead, we take the product. So this is the same as let's say pi p to the power of minus n minus 1 AP pi p to the power of minus n and p. And this is just 1. So what I'm trying to say is that since the difference between adults and K is that adults, everything is localized at P's. So when you want to compare these two, you can do it separately for different points. For k, you can't really do that. I mean, once you know the properties of a function at finite number of points, they are related to each other because all of these local components are coming from a fixed function. But here the components are independent from each other. And therefore, the only part that really matters is when you have at this particular point P, all the rest are the same, and therefore you get this. And in fact, if I work over a more general field, I should, instead of 1, I should put something like size of P, which is the I have to write here call it normal P or something. So I have to define these numbers, and then when you have a divisor given by sum of ord P, E times P, then the degree of this divisor, instead of just being the sum of ord P of these, I have to multiply with these normal P's. Degree of, I've forgotten what is the terminology for this. So bad. Not N of P, it's F of P. So there are two numbers, ramification index and residue index. And this is called the residue index. Yeah. So that's the only difference that you have to be careful when you generalize the Riemann-Roch theorem from an algebraically closed field to a more general field. You have to remember that the degree of the divisor should be defined properly. And the proper way of defining this degree is this way that I'm telling you. Okay, now there is a theorem in linear algebra that I'm going to leave for you to contemplate. Linear algebra. And this is this. Suppose you have A that contains B and C, 3 subspaces of a vector space, and the dimension of A over B is finite. Then dimension of A over B is equal to the dimension of A intersection with C divided by B intersection with C, plus dimension of A plus C divided by B plus C. This is true in general. I'm not assuming that A, B, and C are finite dimensional subspaces, only I'm assuming that the quotient space is finite dimensional. And I'm writing this lemma in linear algebra in order to be applied for this case. Now, let's try to apply it here. Let's suppose P1 is bigger than or equal to P2. So A of P1 is a subspace of the adults that contains A of P2. And And I just calculated for you the dimension of the quotient. Here is the difference of the degrees. Dimension of A of D1 divided by A of D2. D2 is the degree of D1 minus degree of D2, which is finite. And therefore, all the things are ready for me to apply this lemma if I only tell you what I should pick for C. And the thing I want to pick for C is dictated to me by the relation between these A of D and L of D. Because remember, I'm trying to prove Riemann-Roch theorem, so I'm getting a little bit far away from Riemann-Roch by telling you all these abstract things. But A of D is really related to L of D by this intersection. So if I take C to be K, this is a vector space over C of infinite dimension, it follows that L of D1 minus L of D2 is equal to degree of D1 minus degree of D2 minus A of D1 plus K, A of D2 plus K. Okay? Just think of this as the dimension of this quotient, and I am writing this. I take this to the beginning because this is what is important for me, the difference of L's. And therefore, we get a result like this. And now, here's another lemma. The dimension of A divided by A of D plus K is finite. And therefore, let's call this I of D. So finally, I have arrived to the point where I have defined for you this notation that was at the very beginning of this second part of my talk. I said I of D is the degree of a speciality of D, is the dimension of the space of obstructions to Mittag-Leffler problem. It's also the dimension of this cohomology group. And here I'm telling you what this degree of speciality of a divisor is this dimension. And once you know that this is finite, then you know that L of D1 minus L of D2 is degree of D1 minus degree of D2. And now this can be written as, I don't want to make a mistake, A of D1 plus K divided by A of D2 plus K can be written as A divided by A of D1 plus K, A divided by A of D1 plus K. Right. So this is the dimension of this is I of D2 minus I of D1. So what we get is L of D1 minus I of D1 minus degree of D1. So it's better to write it this way. Degree of D1 minus I of D1 minus L of D1 is degree of D2 minus I of D2 minus L of D2. anytime D1 is bigger than D2. Yes. But the fact that D1 is bigger than D2 is not really important here, because any two divisors, D1 and D2, you give me, you can find another divisor D3 that is bigger than both of them. And for each of them, the difference degree of D1 minus I of D1 minus L of D1 is equal to that thing with D3. And the second one with D2 is equal to that thing with D3. So they're equal. So using a very simple argument that given any two divisors, D1 and D2, there is D3 that is bigger than D1 and is bigger than D2. You can actually prove this for any two divisors. So that means that this is an invariant, which is equal to some number. And what this number should be, well, it's better be something related to the genus. This is defined to be 1 minus g. And the reason for that is that have I written this correctly? Degree. I'm just trying to see, because I know that I of 0 must be equal to the genus. So when I put D1 equal to 0, this becomes minus g minus 1. So because L of 0 is 1. And this makes me worry. Maybe I did write this. D1 minus L of 2 degree. Yeah. So let's leave this for you to decide what it should be. I'm a little tired now, but we are not too far away from Riemann-Roch theorem. Let me just rephrase what we have proved. We have proved that L of D is degree of D plus 1 minus I of 0 plus I of D. Why we have proved this? Because I have shown to you that degree of D minus I of D minus L of D is the same thing with D equals 0. And this is minus I of 0 minus 1. And therefore, if I take these to this side and that to the other side, I can find this equation. All right. So during this process, there were several things that I didn't prove. The most important one was the fact that this space was finite dimensional. So we did not prove that dimension of A over A of B plus A is finite. And this space that you see here is exactly what I would call the space of obstructions to Mittag-Leffler problem. And again, I want to leave this for you to think about. But why this space is the space of obstructions. Ultimate left problem. Another thing that you should think about, for those of you who know sheet cohomology, is that why this space is isomorphic to the H1 of X with OX of P. Now, I want to try to tell you why, up to here, nothing about holomorphic one forms or meromorphic one forms appear. But I now want to tell you a little bit why holomorphic one forms actually make appearance. Why do holomorphic one forms make appearance here? This is actually the contribution that Roch had to the problem. So if you give me I want to make a pairing between this space and C. The pairing is like this. If you give me a holomorphic one form, omega, and a collection of local components, Fp, I send it to the residue at P of Fp times omega. Now this is a bilinear map, and it's well defined because almost all of these Fp's are holomorphic. So when you multiply it by omega, they have no residues. And so therefore this is a sum of a finite sum, only finitely many terms are non-zero. And in fact, if something is in here, it will go to zero. And the reason for that is that the sum of residues of a meromorphic one form is zero. Because if something is in K, when you multiply with omega, it becomes a meromorphic one form. And therefore the sum of residues is zero. And therefore you get a map from omega 1x into the dual of A over A of 0 plus K. In a similar fashion, you would see that if I take this is the same as F omega, where F is in L of K minus B. If you have an element in here, it will go to the dual of A over A of D plus K. The reason is that you only need to check that it's well-defined, and the well-defined property comes from the definition of A of D that I already defined. And it's not too hard to see. It's easy. It's really easy. I mean, I just don't have enough time to tell you, but if you think yourself, maybe for 10 minutes, you will find that this map is onto. This map is onto. And this, as one implication, as one consequence, it implies that the dimension of this space is finite. I said one important thing that I didn't prove was that the finite dimensionality of the space, it follows using this idea of Roch. And another application is that L of k minus b is bigger than or equal to I of b. Right? So one application of this is that this space is finite dimensional. The other application is that the dimension on the left-hand side, which is L of k minus d, is bigger than or equal to the dimension of the right-hand side, which is defined to be I of d, the degree of speciality. And trying to convince, in the last 15 minutes, I'm going to convince you that this inequality implies Riemann-Roch theorem. This implies Riemann-Roch theorem. Now, let's see why. Well, what did Riemann prove? Riemann proved that L of t is degree of t plus 1 minus I of 0 plus I of t. I of t is smaller than or equal to degree of t plus 1 minus I of 0 plus L of k minus t. Now this implies that L of k minus t is smaller than or equal to degree of k minus t plus 1 minus I of 0 plus L of k. L of t. And this is 2g minus 2 minus degree of t plus 1. I of 0 is g. Let's take this for granted for a moment. Plus L of t. And this is equal to g minus 1 minus degree of t plus L of t. So I also know that I of t is bigger than L of t is bigger than I of k minus t. Sorry, I'm getting a little confused here. But believe me, this is just some straightforward calculation. I'm going to show that L of t is bigger than or equal to L of t at the end. And whatever remains in between must be an equality. And one of the terms that remains in between is the term that I have in Riemann-Roch theorem. And that way the Riemann-Roch will be proved. But let me do it one more time. Okay, new attempt. So recall what we have proved. We have proved that L of k minus t is bigger than or equal to I of t. Similarly, L of t is bigger than or equal to I of k minus t. We also have proved that L of t is degree of t plus 1 minus I of 0 plus I of t. And similarly, L of k minus d is degree of k minus d plus 1 minus I of 0 plus I of k minus d. Now, I want to use these two equalities and these two inequalities in order to prove Riemann-Roch theorem. L of d, degree of d plus 1 minus I of 0 plus I of d. This is less than or equal to degree of d plus 1 minus I of 0 plus L of k minus d. L of k minus t is this. Is equal to the degree of d plus 1 minus I of 0 plus degree of k minus t plus 1 minus I of 0 plus I of k minus d, which is less than or equal to degree of d plus 1 minus I of 0 plus degree of k minus d plus 1 minus I of 0 plus L of k minus d. And once you do the calculations, you will see that this will imply Riemann-Roch because I already know the degree of k, and you have I of 0, that's 2g, and you have 1 plus 1, that's a 2. So these all cancel each other. Yeah, this is the L of d, not k of minus d. And this minus degree of d will cancel this. So you get L of d is less than or equal to L of d, and therefore everything must be equal in between. Namely, we must have equality here with this. And that's Riemann-Roch. I mean, you can define, what you need to know is that I of 0 is g, but this will follow from the fact that the dimension of holomorphic one forms on X is the same as the genus. Now, I proved this also in the previous lecture using a little bit of Hodge theory, telling you that H1 of X with C is going to be equal to the holomorphic one forms and holomorphic anti-holomorphic one forms. But this can be also proved using easier methods. And I'm going to leave this for you to go and look about the easier proofs. So I'm going to finish my exposition of Riemann-Roch here. But I want to tell you that this second method that I used has the ability to be generalized to more general fields. And this generalization can be found in the book that I mentioned in the previous lecture. Let me write it one more time for you. There's a book by Parkin called Algebraic Numbers and Algebraic Functions. And if you go to that book in chapter 14, you can find two different proofs for this fact, for the Riemann-Roch theorem, that both of them are true for any field, not just necessarily algebraic fields or even C. And the proofs are given in terms of this notion of Adels that I just told you about, and this notion of A divided by A t plus K, which is a space dual to differential forms. So in that book of Artin, there is a very abstract way of defining differential forms that has nothing to do with analysis. It's just using the ring of Adels. You might say, okay, what is the advantage of doing this? Why don't we just work over complex numbers? Everything is nice and that. The reason is that there are some number theoretic applications of Riemann-Roch when you work over a general field, uh, like over a finite field. And for example, Andre Bay himself gave a proof of Riemann hypothesis for curves using this Riemann-Roch theorem. So there is a proof of Riemann hypothesis for function fields over finite fields, but one-dimensional case, the case over when your variety is one-dimensional. The higher dimension case, of course, you probably have heard that was a dream of Grothendieck to prove, but he wasn't managed to prove it. And finally, Deligne gave a proof using a program not following what Grothendieck had intended for it to be proved from. And that made him very angry. And some people say that's one of the reasons that he quit mathematics. But I don't know whether that's true or not. Okay, so I'll stop here. Thank you.
In the last inequality that you wrote, I think one of those plus ones must be minus one, so otherwise they don't cancel.
No, they do, because degree of k is 2g minus 2. And then you have 2 plus 1s, so the minus 2 and plus 2 cancels.
Okay, okay.
Yeah. Yeah, everything in the last, these few lines is completely formal. There is no ingenuity in any of these. The only part that requires really some creative mind was this relation between differential forms and the space of obstructions. And this is something that we saw in the beginning of my lecture, that I use differential forms to find the dimension of the space, dimension of the image of that residue map. So it's very similar to that. Of course, I told you, I have found maybe 5 or 6 different proofs of Riemann-Roch, and they're not entirely different. They are related by, the main ideas of all of them are the same. The notion of residue somehow exists in most of them, and the notion of the fact that this product formula holds, this sum of the or P of F is equal to 0. So these are very important facts that appear in almost all the proofs that you see for Riemann-Roch here. خب بچه اگه سوال دیگه